you're talking of like 75 kilowatts of average power or something, and then peak power is 150 kilowatts. So in your latest Blackwell racks, it's 150 kilowatts of that peak. But what they have to do is, because of the excess headroom you need almost 250 kilowatts of power. And that's basically what you have in an NV72 AI rack, right? It's gone up like 25 times in like 5 years. And we just heard from NVIDIA that they're going to a megawatt in a rack in the next 2 years. That's insane power density rises.
Welcome to another edition of Not Your Father's Data Center. I am Raymond Hawkins, your host. Once again, we are going to talk about technology. Today, we are joined by a friend of the program all the way from Cambridge, England, Dr. Sai Shivareddy, the CEO and founder of Nyobolt. They do batteries, and he's going to explain to us how we might want to hang on to some of the energy that we have and how that might change what we do in the data center. Doctor, how are you today?
I'm great. Thank you, Sai. So nice to meet you.
All right. Well, we'll go with Sai the rest of the way if you're okay with it.
Yeah, that's great. Please.
Sai, you're in Cambridge today recording, right?
Indeed. Yep.
All right.
It's getting cold, but not as cold as probably where you are.
Well, we're doing all right still. I'm in the southeast, so we get a little bit longer hang on to summer, but we'll enjoy a very brief winter where I live, for which I'm very grateful. So, Sai, if you don't mind, can you give us a little bit of insight into you before we get into Nyobolt and what you guys are doing on the battery technology side? Can you back up and tell us, where'd you grow up? Where'd you go to school? How'd you get to Cambridge? You go back as far as you like and give as much detail as you like, but we'd love to hear a little bit about you before we get into batteries and the data center space.
Absolutely. So I was born in India. I grew up there, went to school, at least like middle school, high school there, and also an undergrad program, studied physics, naturally curious about the world around me and how it all came together. So try to dig as deep as possible, and normally you end up doing a PhD if you try to go deep. I found myself on a scholarship to Cambridge because there was a history there. We spoke about some history in the past, and the university goes back 800 years. And growing up in India, there was a stronger connection to the UK, just historically, right? So I had somehow met a professor who brought me on, and yeah.
Help orient us. What year was this? What year did you to leave school in India and go to the UK?
Okay, so this was over 20 years ago.
Okay.
About half my life been in the world of research and materials and energy. But before that, I had no clue where I would land. Everything, science was interesting, but the thing that was changing and, felt interesting was both the new world of energy and the power that would drive the next century. This was turn of century around 2000.
Right. 2000,
so
right.
There was that world of tech. And then there's a world of the infrastructure around, obviously climate and energy were front and center after that first decade. So that influenced like what subjects I selected, or at least you feel like you can do something useful. So either you figure it out along the way, or you kind of see, okay, this is a general direction. And so there was nanotechnology at that time, and nanomaterials, and this was a very big popular science at, around 2000. There was a lot of discoveries in new materials at the nanoscopic level that could fundamentally change many fields, right from photonics and computing. Actually, that's a big part of what I was excited about Cambridge too. So this was 2007-8, and I got this PhD. This department was looking at the 45 nanometer node. So you're talking about semiconductors and data centers. There was some connection between semiconductor processes, materials that worked at the nano level. And we talk about the 2 nanometer node now. Back then it was 45 nanometer node. That was a big milestone. And obviously all the downsizing of chips and the power going up. To me, that was very exciting to get into and see how deep you could go and see how you could change things, because you actually try and understand how things are the way they are.
So what specific, I don't know if the terminology is the same in the UK, what specifically was your doctoral thesis?
So it was on nanomaterials for energy storage and conversion.
Gotcha.
So I ended up on the energy storage front, and I think that's probably why you got me on the show.
Has something to do with what you do professionally. Very good. Okay. Gotcha.
It did not directly take me there straight away after, but it did feel like I could contribute uniquely to progressing the industry at where it was based on some of those learnings. But it's not a straightforward journey because, what you do in the lab never scales. And I think that's one part. It's fundamental to a startup company's early journey. So essentially the research that people do within university labs or in companies' research labs, there are things that stay in the lab, and there are a lot more things that stay in the lab than make it to the real world. And there are many reasons why they actually don't make it, right? So it's fascinating to see which ones do and which ones don't. So there's like an overlap between research done in universities and research done in sort of commercial labs, whether they're in companies, or there is a certain direction you're going where you may or may not know the outcome, and that time frame is sort of indefinite. In the university labs, it's you never know when you have a breakthrough, but you only have money for a certain period. So, you either you get there or you don't, because usually a project's funded for a certain time. And, but the answers to some of these scientific pursuits don't happen in that window. And that's when, commercially and academically, either they align or they don't, and either they click, you make a lot of progress and, get a product out there, or you never get there, right? So I've seen this over now a 20-year period where there's so many things that people want to do in the university labs or just academic environment. They may never see the light of day, but, some things can accelerate those innovations, and other things just come through rapid iteration and people's experiences.
So our world in the data center space, the number one thing everyone talks about today is access to large scale power, right? It's shocking to me how quickly the demand for power has grown, how the demand for access to power has changed where we build data centers. And generally here in the US, that's on the grid power, because we've got a little more land, a little more power than our friends in Europe. So really, really large projects getting really located because of access to large power generation. However, generation isn't global, right? It's not everybody can drop a data center in the middle of Wyoming and get a couple of gigawatts of power to it. So we recognize that's a unique demand profile and supply profile in North America that doesn't exist everywhere else. So then we're asked lots of other, okay, how do I get enough power? How do I hang on to enough power? And I would love to hear how you guys and Nyobolt are connecting what you do back to the data center business, because it is without a doubt the number one subject in our business is how do we get enough power? And so much so that there's microgrids have been talked about, and being able to put power back on the grid, because in the data center world, right, we need power 24/7, 365. We can take no downtime. So we always have everything redundant, but yet the grid has times where it has spikes, at least here in North America, right? Summertime, there's spikes. And so we're trying to put energy back on the grid at times. So there's all kinds of conversation for us around how do we manage power? How do we manage the grid? I would love to hear how you at Nyobolt envision battery technology and improved battery technology fitting into the data center space.
So at Nyobolt, we founded the company, myself and my co-founder, Professor Claire Gray, here in Cambridge University. We set out with a vision to reduce the wait times to recharging batteries. So we invented this new material that allows a battery to recharge in under 5 minutes and do that repeatedly without catching fire, as you've seen in many cases, or actually having a lot more density than is possible. And then these are key aspects of like data center and power. Like power density is critical here. Like you need a lot more power per unit volume than what was in the past in terms of traditional cloud data centers, right? So our core breakthrough has been on the materials front, where you can recharge essentially an energy storage device in as little as like microseconds, obviously not fully, but you can get the fastest energy input and fastest energy output. So the rate of energy flow is power, right? So,
and is that battery agnostic side? Because you're saying, so you're talking about getting the energy into the battery. Can I use, and I'm not saying any battery, but is it, I could use any rechargeable battery and get the charge? And people think of their cars, right? That's probably the one that the people are most interested in.
So Nyobolt makes batteries that recharge extremely fast.
So it's your battery technology and your charging technology.
And our invention on the materials that goes into the battery cells enables our batteries to charge fast. So it's actually a materials limitation that we've overcome and solved as a
in
problem.
the battery.
In the battery. So, we were talking about materials for energy storage, as I said in my PhD days 20 years ago.
Yeah.
So my co-founder and I looked at all kinds of materials over the last decade in terms of how you can get the energy in extremely fast, overcoming the traditional problems lithium-ion batteries had. And they still have those. Usually it is bottlenecks in charging because it heats up too much, and too much heat's not good, right? Fire and other things, thermal runaway. If you could solve that problem on the input power density side, you would end up with some kind of a symmetric charge-discharge profile or an input-output power profile. I mean, you probably are aware about capacitors and other forms of energy storage systems, but while they have more rate of charge, like they can charge very fast and discharge and like symmetrically with very high power, they have very limited energy stored inside them. Like, let's say it's in the microseconds to milliseconds level. So, every power supply has these little passive energy storage units like capacitors and inductors, right? To do that switch mode power conversion. It's a bit of energy stored and then it's chopped to like get you DC output. These capacitors have like, I think 3 orders of magnitude lower energy stored inside than lithium-ion batteries. But I think it's between 3 and 6 depending on the type of pure dielectric film capacitor, like these other types of electronic capacitors, multi-layer capacitors and electrolytic capacitors, and then there's supercapacitors, and then we start getting into the battery domain of like seconds, right? So it's like a fast response energy. You have everything from like microseconds to milliseconds to seconds and to minutes and hours, right? So we looked at it from the microsecond level in terms of fast response all the way to the minutes level in terms of, full storage of that energy in that device in under 5 minutes. That's exactly how we get a rapid charge in 5 minutes, because we looked at the materials that were the limiting factors.
I'm going to ask you to back up, if you will. In my business, the idea of batteries inside a UPS, pretty normal. We're all used to that. People, hey, my power system's gone down. My generator's not online yet. My UPS is going to give me some power to my compute so my compute doesn't go down. Why my generator spins up? Because I've lost utility power. So in the world of data centers, we're all really comfortable with that notion, but we're getting, 6, 7, 8 minutes of runtime out of that massive room full of batteries. And those batteries, before they became lithium, what were they?
Lead acid.
Yeah, so they were all rooms full of
They
lead
still are,
and
right?
acid,
Yeah.
and rooms and rooms and rooms full of them that all had a diminishing life, right? Because on day one they might have given me 7 or 8 minutes, but at year 3 they might give me 3.5 or 4 minutes. So our industry and our listeners are pretty comfortable with the notion of, hey, what's in a UPS? That lead acid, how much runtime? It's got a useful life. It goes away. Then we started making the switch to lithium. And lithium started offering unique solutions and unique problems. Can you help us talk through the switch from lead to lithium, and then help us talk through some of the limitations of lithium?
Great. So that actually comes from, I was talking about time scale. So I got to the minutes level. And what I was talking about was input power in the minutes. So if you start with what you have today in those big UPS systems that had lead, they took like 8 hours to charge, not 8 minutes.
Right.
They could discharge in 8 minutes.
Well, my discharge was an 8-minute window. That's right.
But the recharge times of lead acid is like overnight, right? 8 hours,
right?
Whatever. So you can't do very much with that UPS system if you took 8 hours to recharge it. So
it's kind of a one-shot wonder. Yeah, I get one shot, and then tomorrow it'll be back online.
So depending on how you design it, you have redundancy there, and you put very many of those units to make
a room full
ones
of
available,
batteries,
the other ones not, right?
Yeah,
correct.
Yeah.
So just to give you an order of scale here, so lead acid has energy stored per unit volume of around 20 watt hours, 20 to 40 watt hours. Lithium-ion has 200 to 400 watt hours per liter.
Okay.
Yeah, so factor of 10. For every 10 of those,
so it's 10x the capacity. Okay.
Yeah. Lithium-ion, traditional lithium-ion has this higher energy density, but it comes with the increased energy stored per unit volume problems. That is, how do you manage for the thermal?
It's hotter.
Yeah.
In a non-scientist guy's mind, it's just hotter, right?
It is hotter, exactly.
So I got the same amount of energy in a tenth of the space. It's freaking hotter. And now I got to manage that problem.
Yeah. And lithium-ion can charge faster than lead acid So, you can get 1 hour charge. Some of your best devices out there can charge you 80% in 30 minutes now, right? Like whichever device you use, like a phone or even your EV.
Right.
And even within lithium-ion technology, there's like different flavors with various trade-offs. So you want to store more or you want to run longer. It's called an energy cell. And if you wanted to use for fast response, it's called a power cell. So those types of power cells made it to the UPSs of today. Or a more, let's say, a recent derivative of that has been the battery backup units, or what they call BBUs, right? In some of the large hyperscalers. So, and the big difference between these two is UPS is AC input, AC output, right? It's giving you that sinusoidal good power quality and all of those power smoothing aspects on the AC front. Whereas battery backup units are all DC and it's just for backup. It's not for power smoothing or things like that, right?
Yeah, it's not cleaning up my power at all. I'm just straight DC.
Yeah. So I think a lot of these old, or not, I wouldn't say old, let's talk about like cloud with CPUs and normal servers versus AI servers, right? So I think that's where the big difference is coming in terms of the differences in the load and how that affects not just, the density, but all aspects of safety and whether they can actually do the job. So lead acid was pushed out because the density was not good, right? Energy density was not good. It could give you that backup, but you still even had a lot more needed to get the same amount of work.
And the useful life was so deteriorated so quickly.
Yeah, exactly. You couldn't have full, depth of discharge cycling, which lithium-ion offers. Now, in the last 7 years, you've had a lot of lithium-ion batteries come in. Because lithium-ion intrinsically has higher energy density, and the old materials that were used on the anode side, so this is a negative electrode inside the lithium-ion battery, it's usually a graphite form. It's not as safe when you use that over a period of time, charge, discharge. So you're normally floating. Let's say if you want the UPS to function, it should be fully charged all the time and hold that charge. When the grid fails, that time you discharge for your 5 minutes or so, right?
Right.
Until the backup generators come on. So because they're held at that high potential all the time, high potential is not good. Essentially, the materials inside tend to react more at a higher potential because it has high potential.
Right. They're stressed out, for lack of a better term. Yeah.
It's a bit like, you have a glass and you pour it full and the slightest perturbation spills something, right? Whereas if it's below, it just, shakes inside and it's not spilling outside. So think about the potential of lithium ions going into the electrode. That's if it's full. Even if you just hold it there, the slightest perturbation in terms of what's going on the other components inside the cell, they tend to react and cause side reactions. And these side reactions over time just get worse and worse and worse because it's always held at full potential, you see? Unlike your phone, which, you charge it overnight.
Yeah.
The car, you charge it overnight and then you drive or you use
Spend the whole day running it down.
Yeah, it's not average held at full potential. Like the battery in the data center. So it's not comfortable doing that. Let's just put it mildly, right? As a result, you have degradation pathways or essentially side reactions that cause impedance growth over time. Impedance growth means essentially more heat when you discharge it, and that as resistance increases, the I square R losses or the current losses over that resistor causes more and more heat when it's discharging, and that's one pathway for like an unsafe state. And there are these aspects of unsafe lithium-ion states that you don't want to be in, and they were okay, but if you don't get it right, you have nasty fires across the whole data centers, and you've seen that in the past.
Customers get upset when that happens, just as a heads up. Yeah, when the data center catches on fire, they get really mad at us.
Yeah. So again, this is why people don't like lithium-ion, right? Absolutely. This is just like millions of dollars of assets.
Well, I mean, you're nailing it. Everyone got excited about lithium-ion, and then we said, well, wait a minute, there's an entirely different risk profile here. Yes, there are some advantages, but the risk profile is extreme. So I'm excited to hear what's next after lithium-ion, because it was viewed as, hey, this is a great answer, but pretty quickly the heat made it not terribly practical.
Yeah. So there's that part of heat, and then there's this transition to AI data centers. So cloud has a need for backup, right?
Mm-hmm.
So that's steady loads. And now you have these highly dynamic workloads. You've got 180%, you've got 20%, 180%, like 20 times a second. So if you're doing like training workloads, you have these fluctuations, right? Like you have the GPU, which let's say is 1 kilowatt. To contrast it with a normal cloud data center, let's say you have 1 kilowatt, it was not a CPU, it was like 100 watts or something, but let's say you have 1 megawatt of power, or let's say the average cloud 10, 20 megawatts, let's say 20 megawatts, so you could have 2,000 of those CPU-based systems, or 20,000 if it was 100 watts. It's actually big for CPUs, but small for GPUs.
Right.
So what we're looking at is the same GPU, while its average power is 1 kilowatt, its peak is almost 2 kilowatts, or 1.8. For a short duration, which was in the past a transient, but these transients have become bigger and bigger. You're talking of like 75 kilowatts of average power or something, and then peak power is 150 kilowatts. So in your latest Blackwell racks, it's 150 kilowatts of that peak. But what they have to do is, because of the excess headroom they need, you need almost 250 kilowatts of power. And that's basically what you have in an NV72 AI rack, right? And you contrast that with your normal CPU server in your normal data center, which was not even like 10 kilowatts per rack. You've gone up like 25 times in like 5 years, or whatever, right? Since the first GPUs came, maybe it's like 8 years or so.
Yeah.
And we just heard from NVIDIA that they're going to like megawatt in a rack in the next 2 years. That's insane power density rises, right? I'm sure you've covered like aspects of cooling and all that.
There's all kinds of trouble at the idea. I get in a lab in California. Hey, I'm going to have enough GPUs in my rack that it needs a megawatt to run it. But there's so many other ramifications, cooling being one, right. Safety being one. How do I have that much electricity in that small a form factor and it'd be safe for humans to work on? There's just all kinds of questions coming.
So I think in the last like 12 to 24 months, so I was talking to a co-location provider, or a virtual CPU or virtual machine provider recently, and they had like this data center in Phoenix where you had a cloud side that I think was 10 megawatts, so you could have your steady loads at 10 megawatts. And when they thought, okay, we can put 10,000 of these GPUs, each one kilowatt for 10 megawatts, they couldn't. They could only use 5,000 because of these peak problems.
Because of the spikes.
5 megawatt goes to 10 megawatt spike. So you've got like millions of dollars of assets that you've acquired thinking that's what you could fit in, and they didn't even know that they could not do it until they fit the machines in, the racks inside. You sat on that inventory that you can't use, right? So you've heard this many places, or you could use that 10,000 but throttle it down to less than 50% utilization to have that headroom. So these problems are very different from, first of all, power problem. Like one is steady load, other one is a highly dynamic peaky load. Now, how do you design a data center for native peaky loads? It looks very different. You can't use the lead acid UPS systems because these peaks are ultra fast and like these transients, they have like tens of amps per microsecond, or and essentially this slew rate of the DIDT that you need for bringing these GPUs switched on, the latency increases the longer the cable is because of the inductance.
Right.
And like that's basically like DIDT, the slew rate that limits.
Every meter counts.
Exactly.
It impacts it. Yeah.
So essentially, you may have what is on paper great metrics on the ratings. Okay, power taken care of, but actually that's just static loads. For dynamic loads, there were no metrics. There's no like continuity of compute metric. You can call an uptime of like power is available at that site, but actually it's breaking when the GPU needs it. So you are having brownouts, you're having blackouts.
When it spikes and's asking the most, that's when we start to get strained. That's exactly right.
Yes.
All right. So tell me how Nyobolt helped with that.
So coming back to fast energy storage, you need microsecond level peak response to just like come on as fast as you can. You can recharge it again as fast as that window is available. So there's 20 milliseconds of like overshooting by 100% or something, 80%. Yep. And then there's another like maybe 100 milliseconds or a few seconds. So you know how the workloads are trained, right? So you have the compute cycle, and then you have a communication cycle, and then you have like a checkpoint cycle with the memory. So each time you're going up and down, it's a repetitive pattern. And you, of course, you can't predict it fully, but
you certainly get a rhythm for what's coming.
Correct.
Yes,
correct. So if you look at a moving average over 5 seconds, you need to be able to like discharge 20 times a second and charge across that 5-second window. So you're net neutral. So you're not actually depleting the energy while you're doing it. The bigger problem here is the grid is not able to give power fast enough for
That's right.
training.
My traditional delivery system can't bounce up. I mean, right? The way a grid works, it has to be stable. It has to have predictable workload. It has to have balance between production and utilization. That's how the grid stays balanced. But whether it's 60 hertz or 50 hertz, doesn't matter. We got to stay balanced. So I can't come and say, give me 20 megs. And oh, by the way, I'm going to give it back to you in about 2 seconds. I can't do that to my grid.
Yeah.
So how tell me how you help me, because that is a real problem we are all designing for right now.
Yeah. So anyway, we're at the core of that problem from the way power is transferred, right? So you have medium voltage coming in. I mean, you mentioned like DC microgrids going through. So the new architectures are moving to higher and higher voltage to get the power up, not increasing current, keeping current fixed. Let's get the voltage up to 800 rather than like 48 volts, right? So what's happening, whether it's the old 48 volts or the new high voltage site, you have energy conversion power conversion, where you have like medium voltage going down to like, let's say 400 volt or 800 volt bus, and then or a 48 volt bus at the rack. And at 48 volts, that rack has not like at the server, it goes on to 12 volts and then 0.8 volts at the GPU for transistors, which normally come on like 0.7 volts, right? So there's a lot of like voltage conversion going on here, and the way voltage and all of the power conversion happens is usually through these switch mode power supplies, right? Or DC-DC converters in this case, if it's just pure DC. Each of those converters need a bit of energy stored to get the right voltage regulation going on. So the capacitors have played that role in the past, and you know how in the beginning of our conversation we said they don't store enough energy. We've invented something that has lithium-ion like energy storage capacity, so that's still more than 10 times out of traditional lead-acid batteries. So we get the 5-minute backup capability.
So it's like a super. Can I call it a super capacitor?
Yeah, and we have super capacitor like power.
Interesting.
So it's sort of bridging the two worlds of capacitors and batteries, and the last 5 years we've just been focused on finding applications where capacitors were used, where high power batteries were used, but they couldn't be charged fast enough, so they swap the batteries out because they can't recharge them in that time frame. We've solved that recharging problem to essentially behave like a capacitor in terms of input power, output power being symmetric.
How quick is that? How quick can we do input back to fully charged?
Again, I mean, full energy is few minutes, right? Like, so if you're recharging in 5 minutes, you can recharge in 5 minutes. Okay. But that's in a backup mode. Yeah.
Okay. But
the peaky workload problem that I was talking about is not a full discharge.
Right. I'm not going to zero. That's right.
Yeah. So there's a lot more system level balancing required, and we've been working on the whole stack here. It's not as simple as, hey, throw that capacitor out and put this thing and it'll work. You need a bit more engineering at the system level.
There's a couple of electrical engineers running around helping. Yeah.
Well, and a lot of embedded layers in terms of the power conversion stack along with the energy storage stack, right? Because essentially a power conversion has a bunch of transistors, switches that are like connected to some energy storage that is just switching on and off to get you a regulated output. So that part and our storage unit, when you combine them, we call this a dynamic response system, dynamic power system that allows you to essentially regulate the voltage output such that the 48 volt bus stays at 48 volts without droop and those that rapid fluctuations. That DC bus essentially saturates the capacitors of the power supply, and it translates to peaks or like transients in the AC part, and the UPS generally doesn't have enough storage there even for these very fast transients. And then when that's not filtered, it starts blowing up substations or transformers and stuff, right? So on one side, you're seeing the hyperscalers and like GPU manufacturers slow things down. So you're getting faster and faster GPUs that have to be throttled. That's not good. You're paying top dollar for a GPU.
Why pay for it that you want to dial down to 70%?
Right?
That's right.
Yeah.
But they're solving another problem. They feel like they have to. Yeah. Sai, can I ask you a very commercially centric question?
Sure.
So I'm a sales guy. So I'm thinking about this in terms of my customers, which I'm sure you are or will eventually. So give me a scale understanding. So what's the biggest footprint, meaning from an energy perspective that you've built one of these? You gave it a name earlier that I didn't catch. You called it what did you call the solution?
A dynamic response power system, basically. So
dynamic response power system. All right, dynamic.
If you have one of the shells, it's called a dynamic response unit.
So give me a couple scale. What's the biggest one you made, meaning measured in power?
At 48-volt level, we've been actually shipping products to a customer, not in the data center, but it does the same function.
Okay.
And we announced this actually 2 weeks ago.
What's the form factor? What does it look like?
So it's actually a box that you plug into a rack.
It is rack mountable.
Yeah. So I mean, we had to like change the height such that it fits in a 1U, and and also change the XY such that either you are like a 19-inch or you're an OCP 21-inch, and how deep. So that part is configurable, but the internal building blocks have our cells and our power electronics that essentially is a power source, regulating voltage output, which can decouple the grid power transients and the grid supply to time of use. So we are kind of time shifting these spikes such that, if you have up, down, separated by whatever time interval, we time shift it so that the grid sees a flat output.
So I don't want you to give away any secrets. You said you're shipping to a customer today, not in the data center business. Do you have data center customers in this conversation yet?
We're having one maybe now.
Yeah, you and I are having one. Yeah, which is we're supposed to be recording a podcast. So I'm going, wait a minute, this is interesting stuff here.
So you're a sales guy. I'm a sales guy.
Yeah.
But yeah, what I'll tell you is this: like this problem was amplified in the last 12 months. Okay.
Yeah.
And the natural place to go to the usual power supply people and say, hey, how can you put more storage inside a power supply? And what do we do? And, and then people are scrambling to go find energy storage units that can go into a power supply that can solve this problem. And we're like, hey, we've been doing this for the last 5 years.
Yeah.
Exactly this type of power problem we've been trying to solve.
It's just been a different application in a different area. Yeah, this is a problem we are wrestling with today.
I mean,
sure.
Look at what's happening at the megawatt in the rack. I mean, we come from a megawatt power system in an EV. We built an EV that can charge at a megawatt and discharge at a megawatt.
Right.
This is a mine haul truck. They run at close to 1,000 volts. As I said, 48 volt in your data center, you're going to close to 800 volts or 1,000 volts, even more if you can. But the industry is looking at solutions that have been deployed in other sectors, like EVs or grid or industrials, where this type of high power density problems are being solved. So you need solutions from other proven sectors. I mean, you didn't have this problem 2 years ago, or
no, that's right. Ago. It wasn't an issue.
Exactly. And big companies that are in this space, or the UPS makers and whoever else, have not reinvented anything in the last, I would say, not to offend anybody, but the UPS, as you know, were invented a long time ago.
It looks like the same it did 40 years ago.
They were
exactly the same
as they were 20 years ago, I will tell you
That's
that.
exactly right.
Having looked at what's been developed over the last 20 years on the material side, as I told you from my background, into increasing power density for the storage systems. And essentially, that's what led to our startup idea and say, hey, how can we do it 10 times better than what people out there are doing today, because they haven't reinvented anything in the last 2 decades.
Well, your business being 6 years old, right? There's some freedom in that, right? You don't show up with a 4-decade history around a UPS that this is how I've always done it. There's some freedom.
You will never talk to me because, this is what new is not good, too much risk. But at the moment, the old metrics for stability are gone out of the window. Big hyperscalers are not using UPS systems. They're out. There's no space for them.
It's not practical. I can't use it. That's exactly right. So, Sai, this podcast probably should have been hosted by either my head of innovation or my head of design, but because I think they're both going to want to talk to you after we do this. This has been really, really, really fascinating. Yeah.
So where we are today is we have a supply chain to build our building blocks. We have a supply chain to produce, 10,000, 20,000 units per year. And I've invested $70 million to just get this going in 3.5 years' time. That's where bulk of the investment went to build capacity.
Right.
We were focused on these sort of adjacent verticals where these power requirements, high voltage requirements were already being disrupted, to use that word, because they were not done before.
Right.
And now that disruption's coming to your world where...
Oh, it's coming. It's here. It's here.
Yeah,
you nailed it, right? The GPU, and by the way, and getting worse, right? Yeah. Because the next round of GPUs are going to even be that much more power hungry, which means the peak and the valley are going to be further apart.
Yeah, absolutely.
Yeah.
And the thing is, as you said at the beginning, we are constrained by power. Like tokens is our power, right? Like our focus at this point has become more like, how can we enable you to use more GPUs per power unit that you have at your site? Because if you want to double it or triple it or like increase it 10 times, you're going to wait for what, a decade? I don't know. In some sites, you probably can't ever. But can we double that today with what we have? Because we're time shifting the power needs at that very fast intervals.
Yeah, I love that. All right, well, Sai, this was an awesome conversation. We're definitely going to have some other conversations that aren't going to get recorded because we're interested in learning about the dynamic response power systems. Really, really cool idea. Really, really cool technology. Love that smart guys like you were thinking about this years ago, because it is a real problem in our industry right now.
So ultimately it's two things, right? Like you want to do more with what you have, and we don't want to like put that extra burden on the society around you and around us.
Right. That's it.
We want to like try and essentially it's efficiency gains from what we already have. And
I can power the data center without having to take more power to do it, right? I don't need to leave that headroom in the space, which is going to help us, because you're right. I mean, at the end of the day, all of us want what we can do on our cell phones. The demand for the applications is there. We've just got to figure out how do we meet that demand with power responsibly. And this seems like a huge step forward. The fact that you get how dynamic the workload is and how quickly it changes will help us as an industry. So excited to see how this goes from here. Thank you so much, Sai, for explaining it to us. Thank you for thinking about it 20 years ago and for building a company around it. And I'm excited to see where you guys go, and excited to see what a partnership with us might look like as well.
Thanks a lot, Raymond. I blown away by the time we spent. I've not had a real conversation, with a potential user of what we've been building, but it's essentially thanks for doing what you're doing, like especially on a show like this where we help get that awareness out in terms of what leaders are doing, like as yourself in the space, to bridge some of these problems.
Awesome stuff.
Yeah, thanks a lot.
Sai, I do have one Cambridge question before we go. I know you told us before we started recording that they no longer run the courtyard. If I come to Cambridge and we get a partnership, can you and I race around the courtyard?
We can do
just
that.
One time. Just one time.
Just one time.
Yeah, well, something about whatever, our discount could hang on who wins the race around the courtyard.
And the best part, I'll take you to that Van de Graaff generator, like the real big one that was.
Yes, that would be even better. Yes.
There's that part of history too, 100 years ago.
Yes. I want a picture with the big Van de Graaff generator at Cambridge. Awesome stuff. Sai, thank you for joining us. We really appreciate it.
Thank you.